Section 1. Introduction. In this video, we'll work through a cubic example, and we'll compare and contrast it to the mostly quadratic fields we've spoken about so far. This will also give us a chance to meet some new interesting results. So in this video, we're going to find all the solutions to the equation x cubed minus 7y cubed equals 1 for x and y integers. Well, the first thing we'll do, as usual, is try to factorize the left-hand side. Inside the complex numbers, it factorizes as x minus lambda y, x minus lambda prime y, x minus lambda double prime y, where lambda, lambda prime, and lambda double prime are the three cube roots of 7 in the complex numbers. Just like in the quadratic case, this expression is the norm of the element x minus lambda y inside the field q adjoin lambda. Here's a picture of the cube roots of 7. One real and one pair of complex conjugates. So we could write this equation as x minus lambda y, x minus omega lambda y, x minus omega squared lambda y, where lambda is one of the cube roots of 7, and omega is a primitive cube root of unity, as always. But this factorization involves both a lambda and an omega, so it takes place in the ring of integers of q adjoin lambda, comma, omega. This is a degree 6 extension of q, and it doesn't have the right norm function anymore. This is easily solved for our purposes, though. If we multiply the second and third brackets back out, we get x squared plus lambda xy plus lambda squared y squared. So now we're back inside q adjoin lambda, the cubic extension we'd hoped for. So in order to apply our results so far, we have to start off by asking, what's the ring of integers of q adjoin lambda? Well, since lambda satisfies a monic polynomial, we know that it's an algebraic integer. So this ring of integers contains z adjoin lambda, so a first guess might be that the ring of integers is equal to z adjoin lambda. Let's find out. Section 2. Norms and minimal polynomials. Let lambda be any algebraic integer now. With minimal polynomial f of x, which is x to the n plus c n minus 1 x to the n minus 1 plus plus c1x plus c0, where all of these ci are integers. Here are two important facts. Firstly, because f is a minimal polynomial, all of its roots are distinct. Q is called a perfect field for this reason. Secondly, q adjoin lambda has n embeddings into the complex plane, let's say sigma 1 up to sigma n, where sigma 1 sends lambda to lambda 1, and so on all the way up to sigma n, sending lambda to lambda n. So, since we know the roots of this polynomial, we can factorize it as x minus lambda 1 up to x minus lambda n, and then multiply this back out and compare coefficients. Okay, they both start with x to the n. The coefficient c n minus 1 is the negative of the sum of the roots, and so on all the way down to c0, the constant term, which is plus or minus the product of the roots. But by the second fact I gave, this means that in particular c0 is plus or minus the product of all the distinct embeddings of lambda. But that's just the norm of lambda by definition. So if we know the minimal polynomial of lambda, we can read off its norm, at least up to a sign, from this coefficient c0. This fact will be important in the next section. Section 3. Eisenstein polynomials. Let p be a fixed rational prime number, and let f of x be some monic polynomial with integer coefficients exactly as before. So the coefficient of x to the n is 1, and we're going to suppose that all of the other coefficients are divisible by p. And moreover, let's suppose that the constant term c0 is divisible by p exactly once. In other words, divisible by p, but not by p squared. In the language of p-valuations, this says that all of the coefficients ci have p-valuation at least 1, and c0 has p-valuation exactly 1. Well, if f satisfies this condition, it's called an Eisenstein polynomial with respect to the prime number p. So here are some examples. The polynomial x cubed minus 7 is Eisenstein with respect to 7. Let me just fill in the missing terms in the middle. Notice that these zeros are divisible by 7, and this 7 at the end is divisible by 7 but not by 7 squared. Okay, another example. The polynomial x to the 4 plus 12x squared minus 8x plus 6 is Eisenstein with respect to 2. Again, filling in the missing term here, we can see that these coefficients, 0, 12, and minus 8, are all divisible by 2, and the coefficient 6 is divisible by 2 but not 2 squared. Okay, here are some facts. If lambda has minimal polynomial f of x of degree n as before, and if f is Eisenstein with respect to p, then lambda to the n is divisible by p. Here's a quick sketch proof. Firstly, by definition, when we plug lambda into this polynomial, this minimal polynomial for lambda, we get 0. So we can rearrange to get lambda to the n equals minus c n minus 1 lambda to the n minus 1 minus ... minus c1 lambda minus c0. And everything on the right-hand side is divisible by p, because all of these coefficients have positive p-valuation. Okay, and the second fact we'll need is the following. The norm of lambda is not divisible by p squared. Well, if you remember that the norm is plus or minus c0, then this just follows from the definition of an Eisenstein polynomial. We've insisted that c0 is not divisible by p squared. So now let lambda be some algebraic integer again, and let k be q adjoin lambda. We know that the ring of integers of k contains z adjoin lambda. Our question is, how far apart are these two rings? For example, we might ask more precisely, what's the index of z adjoin lambda inside OK? Well, suppose that lambda has minimal polynomial f, and that f is Eisenstein with respect to p. And in this case, I'm going to claim that the number p cannot divide this index. Right, here's a proof. Firstly, let me write out f of x explicitly as before, with coefficient ci, where p divides all the ci, but p squared doesn't divide c0, which is plus or minus the norm of lambda. Okay, plugging in lambda as before, we can see that lambda to the n is a multiple of p, which I could write as 1 over p times lambda to the n is in z adjoin lambda. I'm going to use these two facts crucially in our proof going forward. So next we want to prove that p doesn't divide this index. So let's suppose for contradiction that it actually does. Then pick some element alpha, which is b0 plus b1 lambda plus ... plus b n minus 1 lambda to the n minus 1, where all of the b sub I are rational numbers. We're going to suppose that alpha is an algebraic integer. In fact, it will be in some possibly smaller lattice, which I'll call L, but not in z adjoin lambda. And I've chosen this lattice L sitting somewhere in between OK and z adjoin lambda, so that the index of z adjoin lambda in L is exactly equal to p. Now, a similar argument from last video shows that each coefficient b sub I must actually be an integer divided by p. And because we've assumed that alpha isn't in z adjoin lambda, these b sub I are not all integers. So let's suppose that the first non-integer in this list is b sub j. That is, pick the number j between 0 and n minus 1, such that b0 up to b sub j minus 1 are all integers, but b sub j isn't. And I don't really mind where the rest of the coefficients are, but they're all definitely integers divided by p. With this number j in mind, let's multiply alpha by lambda to the n minus j minus 1. Okay, we get the following. Let's just take stock of this. We chose alpha to be an algebraic integer by definition, so alpha lives in OK. Lambda to the n minus j minus 1 is just a power of lambda, so it lives inside z adjoin lambda, which is a subring of OK. All the b0 up to b sub j minus 1 are in z, so these first j terms are in z adjoin lambda, and hence they're also in OK. All the terms from b sub j plus 1 lambda to the n upwards have coefficients in 1 over p times z, but they also all have a factor of lambda to the n, and our first fact in green above tells us that 1 over p lambda to the n is in z adjoin lambda. So overall, all of these terms are in OK as well. So finally, the only term we haven't dealt with is this one, b sub j lambda to the n minus 1. And we could rearrange this equation to write b sub j lambda to the n minus 1 in terms of all the other algebraic integers here using just addition, subtraction, and multiplication. So because algebraic integers form a ring, b sub j lambda to the n minus 1 must be an algebraic integer too. Okay, let's record this fact up here and make a bit of space. Since b sub j lambda to the n minus 1 is an algebraic integer, its norm is a rational integer. And if I multiply it by p, that is, I'm scaling the fundamental cell of this n-dimensional lattice in every direction by a factor of p, then its norm of course goes up by a scale factor of p to the n. Okay, since b sub j has exactly one factor of p on its denominator, this number p times b sub j has no factors of p anywhere. Let's call it k. It's an integer that is not a multiple of p. Now, using the multiplicativity of the norm again, we finally get that k to the n times the norm of lambda to the n minus 1 is a multiple of p to the n. Okay, but the p valuation here is n minus 1, using the fact we established earlier that p squared does not divide the norm of lambda. Whereas to say that it's a multiple of p to the n says that its p valuation should be at least n. Right, that's a contradiction. So this can't happen. We've shown that if the minimal polynomial of lambda is Eisenstein with respect to p, then p cannot divide the index of z adjoin lambda in the full ring of integers. Section 4. Discriminants. Let k be q adjoin lambda, and now we're going back to the special case where lambda is a cube root of 7. We know that the ring of integers contains z adjoin lambda, and we can pick a basis for z adjoin lambda, say the basis 1, lambda squared. Since we know the three embeddings of lambda from the beginning of the video, we can calculate the discriminant of this basis as minus 3 cubed times 7 squared. So remember that this tells us the index of z adjoin lambda in OK could have a factor of 3 and or a factor of 7 in it. Okay, so it could be 1, 3, 7, or 21. But the minimal polynomial of lambda is x cubed minus 7, which is Eisenstein with respect to 7. So by what we've just proved, 7 can't divide the index. We've eliminated 2 of these possibilities already. So we're left with the 2 remaining possibilities, 1 and 3. Well, to work out which it is, let's reparametrize z adjoin lambda. That is, instead of thinking of lambda as the element we're adjoining, I'm going to think of lambda minus 1 as the element we're adjoining instead. So we'll take the basis 1, lambda minus 1, lambda minus 1 squared. This generates the same lattice as the previous basis, so its discriminant is still the same. What's the point in that? Well, the minimal polynomial of lambda minus 1 is x plus 1 all cubed minus 7, and when we multiply this out, we can see that this polynomial is Eisenstein with respect to 3. So we can rule out the case where the index is divisible by 3 as well, and we finally conclude that the full ring of integers was just z adjoin lambda all along. Okay, now we can go back to the equation we originally wanted to solve. Section 5. Units. We want to find integers x and y such that x cubed minus 7y cubed equals 1. Well, let's start off by spotting a couple of easy solutions, for example, x equals 1 and y equals 0, or x equals 2 and y equals 1. Right, we'll come back to those later. In general, elements of z adjoin lambda, where, as before, lambda is a cube root of 7, have the form a plus b lambda plus c lambda squared. And we can work out the norm of this element as follows. So x cubed minus 7y cubed is the norm of x minus lambda y, and just as always, the units of z adjoin lambda are the elements with norm plus or minus 1. So our question reduces to finding units a plus b lambda plus c lambda squared, where this last coefficient c is equal to 0. First, recall Dirichlet's units theorem. Z adjoin lambda has one real embedding and one pair of complex conjugate embeddings, as we saw at the start. So its units are just the finite order roots of unity, that's plus and minus 1, multiplied by some power of a single fundamental unit u. That is, like last time, the units in logarithm space lie along a line. Here's L of 1, L of u squared, and so on. And in the other direction, L of u inverse, L of u to the minus 2, etc. So before we find all the units of a particular form, it would be helpful to start off by finding a fundamental unit u, so that we can generate all the units. Well, we know one non-trivial unit already. The example solution in red at the top of the screen, when x is 2 and y is 1, gives the unit 2 minus lambda. Is this unit a fundamental unit? Let's look for a particular fundamental unit as I'm going to define on this slide. Passing to logarithm space loses some information. There are actually 4 fundamental units here, so let me specify precisely which one I want. Let's assume that lambda is the real cube root of 7 here, so that q adjoin lambda is a subset of the real numbers. Then we get a 2-to-1 correspondence between units in z adjoin lambda and their images in logarithm space. We have the positive units to the right of 0, and we have the negative units to the left of 0, corresponding to that plus and minus 1. Now just for this slide, I'm going to choose u to be the positive fundamental unit which is greater than 1. Now it's not too hard to prove the following. Firstly, the size of the discriminant of z lambda is less than or equal to the size of the discriminant of any sublattice. We gave that as a fact last video. But in the case where L is the specific sublattice generated by 1, u, and u squared, we can bound the size of the discriminant of L above as a real number by 4u cubed plus 24. And in particular, this means that if v greater than 1 is a unit such that 4v to the 3 over 2 plus 24 is less than or equal to the discriminant of z adjoin lambda, then v must be a fundamental unit. The calculation here is quite easy, but it's long and tedious, so I'm not going to give it. The full proof, in case you'd like to look it up, is given in Froelich and Taylor, section 5.3. Now, we know the unit 2 minus lambda, but this is less than 1. So, okay, let's take its inverse. The norm of 2 minus lambda can be written as this product, 2 minus lambda times 4 plus 2 lambda plus lambda squared, and this is equal to 1. So 4 plus 2 lambda plus lambda squared must be the inverse of 2 minus lambda and must be greater than 1. In fact, numerically, when we substitute in lambda as the real cube root of 3, we get about 11.485. So if we plug this value in for v, we get that 4v to the 3 over 2 plus 24 is about 179.7. And we've already calculated the magnitude of the discriminant of z lambda. That was 3 cubed times 7 squared, which is 1,323. Okay, so 179.7 is less than 1323. So by the fact above, this must be a fundamental unit. In particular, if 4 plus 2 lambda plus lambda squared is a fundamental unit, then the inverse, 2 minus lambda, the one we started with, is also a fundamental unit. So from the next slide onwards, I'm going to go back to using 2 minus lambda as my preferred fundamental unit, just because it will make future calculations easier. So, back to our problem. We want units of the form x minus lambda y. Well, 2 minus lambda is a fundamental unit, so every unit is plus or minus 2 minus lambda to the n for some integer n. And in fact, we only want units of norm plus 1, and those are the ones of the form plus 2 minus lambda to the n, where all of the negative units have negative norm. So we're just going to focus on the positive ones. Let's expand 2 minus lambda to the n binomially. We get 2 to the n minus some multiple of lambda, plus some multiple of lambda squared, minus some multiple of lambda cubed, and so on. I'll just write a few of them out. And now let's tidy this up. Firstly, these three all contain a factor of lambda cubed, which I'm going to factorize out. And these three all contain a factor of lambda to the 6, which I'm going to factorize out, and so on. Now we'll replace the lambda cubeds we just factorized out with 7s, and the lambda to the 6s we just factorized out with 7 squareds, and so on. And the reason we did this was as follows. We can now write down all the terms in this sum that don't contain lambda. Then we can write down all the integer multiples of lambda. Then we can write down all the integer multiples of lambda squared. And that's the entire sum. So let me just tidy that up a bit. We want units where this coefficient of lambda squared is equal to 0. So, for which values of n is this coefficient 0? Well, we know two units already. The unit 1, that's 2 minus lambda to the power of 0, and 2 minus lambda, which is 2 minus lambda to the power of 1. So n equals 0 and n equals 1 are two solutions. Are there any more? Section 6. Strassmann's theorem. I actually won't state the theorem in full here. I'll just give you an idea of what it says and outline a proof of it in this case. The question we want to answer is, when is this big sum equal to 0? So let f of t be the function 2 to the minus 2 times t choose 2, minus 2 to the minus 5 times 7 times t choose 5, plus 2 to the minus 8 times 7 squared times t choose 8, and so on. So the sum above is f of n times 2 to the n. Now, you might be worried about this sum. If t is a positive integer, these terms eventually become 0, so this is just a polynomial. But if not, then we get an infinite sum. Let's not worry too much about convergence issues and so on in this video. Actually, everything I'm about to say also makes sense in the case when t is a negative integer, and negative and positive integers are the only cases we care about here. So, what are the integer roots of f? Well, we already know two of them, t equals 0 and t equals 1. So, let's write out these binomial coefficients in full, and take out a factor of 2 to the minus 2 times t minus 1. If you like, you can spot the pattern in this sum, and write the infinite sum more compactly using sum notation like this. Okay, so let's exclude the roots we already know about and assume that both t and t minus 1 are non-zero. So t isn't 0 or 1. When is this factor 0? Strassmann's theorem will tell us that because of the increasing powers of 7 in this factor, it can't have any roots. So t equals 0 and t equals 1 will be the only two solutions here. Let's see how that works. We'll be using the 7-adic valuation function, v7, and we'll want to apply it to this big sum. So let's take a brief digression to calculate v7 of this factorial on the denominator. First, let me just write out a few small cases. When I equals 1, we're calculating v7 of 5 factorial, so 5 times 4 times 3 times 2 times 1, and there are 0 factors of 7 in there. When I equals 2, we're calculating v7 of 8 factorial, and there's 1 factor of 7 in there. When I equals 3, we're calculating v7 of 11 factorial, and again, there's 1 factor of 7 in there. So every multiple of 7 contributes to the 7-adic valuation. But let's be careful. It's not quite as simple as just counting multiples of 7. For example, when I is 18, we're calculating v7 of 56 factorial, so let me write out all the multiples of 7, there are 8 of them. But you might notice that 49 is actually 7 squared, so 49 contributes twice to the 7-adic valuation. This valuation turns out to be 9. In general, when you try to find v7 of k factorial, you count all the integers less than or equal to k that are divisible by 7. These will all contribute at least 1 to the 7-adic valuation. But you also have to count the number of integers divisible by 7 squared, because each one of those will contribute an extra 1 to the valuation. And all the integers divisible by 7 cubed will contribute yet another extra 1 to the valuation, and so on. I'll write this in shorthand using this floor notation. The floor of k over 7 plus the floor of k over 7 squared plus the floor of k over 7 cubed, and so on. Okay. We wanted to work out v7 of 3i plus 2 factorial. So let's plug in k equals 3i plus 2. Now we're not going to be able to get a nice formula for this, but let's take a crude approximation. Firstly, this expression is less than 3i plus 2 over 7 plus 3i plus 2 over 7 squared plus 3i plus 2 over 7 cubed, and so on. That is the same expression without the floor signs. Now, 3i plus 2 over 7, I'll just leave that the same. 3i plus 2 over 7 squared is less than a half of 3i plus 2 over 7, because a seventh is less than a half. 3i plus 2 over 7 cubed is less than a quarter of 3i plus 2 over 7, because 1 over 7 squared is less than 1 over 2 squared, which is a quarter. And we just carry on like this. 1 copy of 3i plus 2 over 7, plus a half a copy, plus a quarter of 1, an eighth of 1, a 16th of 1, and so on. This is a geometric series, and it sums to 2 times 3i plus 2 over 7, so 6i plus 4 over 7. And you'll notice that when I is at least 4, this is bounded above by I. So, v7 of 3i plus 2 factorial is less than I when I is at least 4. But in our earlier examples, we showed that this was also true when I equaled 1, 2, and 3. So together with this, we've shown that v7 of 3i plus 2 factorial is always less than I for any positive integer I. Okay, this is the fact we need. So let's finally go back to showing that this factor can never be 0. Well, suppose it is. First of all, v7 of a half is 0. Okay, now let's deal with the term inside the big sum. v7 of all of these factors of 2 is 0, and v7 of all of the factors of minus 1 is 0, so they don't contribute anything. I'm just going to get rid of them. The expression on the top of the fraction is an integer, so v7 of it will always be at least 0. v7 of this 7 to the I is just I by definition, and we've just shown that v7 of what's on the bottom of the fraction, 3i plus 2 factorial, is less than I. So in total, we have I or more factors of 7 in the numerator, and less than I factors of 7 in the denominator. That is, in total, this term has positive 7-adic valuation. You can cancel out all the factors of 7 from the denominator and still be left with some in the numerator. Okay, now each of the terms in this sum has positive 7-adic valuation, so by one of the facts I gave you last video, this whole sum has 7-adic valuation greater than 0. Now combining this with the term of a half up front, since I'm adding together two things with different 7-adic valuation, the 7-adic valuation of their sum, the whole of the left-hand side, must be the minimum of those two, which is 0. But this is a problem because v7 of the right-hand side is infinity. Okay, this is a contradiction. This expression can never equal 0. So finally, we have our conclusion. The only two solutions to the equation we started with are x equals 1 and y equals 0, and x equals 2 and y equals 1.